So we've completed 8 weeks, we're starting 9 weeks, and now is where we really start to get into what's going on during exercise. We've alluded to some things, but now the focus, especially as we go through these next several weeks, is what's going on during exercise. So we're going to talk about today, with these 3 lectures I believe there are, we're going to talk about what the cardiovascular system does to adjust during exercise, and then on Thursday, we're going to talk about the challenges that the respiratory system faces and the adjustments it makes. And so here are the 3 objectives that we're going to get through today. So when it comes to cardiovascular adjustments during exercise, there are 3 things that must occur if we're going to maintain exercise and exercise intensity. And it's important to note that when we're talking about this, we're actually talking about vigorous, large muscle mass, okay? So things are a little bit different if it's not large muscle mass. So we're thinking in terms of like running, cycling, that sort of thing. So the autonomic nervous system has to change what it's doing to increase cardiac output, okay? We have to, not only do we have to increase cardiac output, but we have to change where that cardiac output goes. But we also need to get the blood back to the heart in the same proportion as that increase in cardiac output. So for example, if I'm sending 25 liters a minute out of my heart, I need to make sure that I'm getting that much back to my heart. Okay, and so just to kind of go along with this, remember our resting cardiac output is about 5 liters a minute, and there's a linear relationship between intensity, which we can do in terms of percent VO2 max, and cardiac output. Now, depending on who you are, what kind of shape you're in, that sort of thing, cardiac output can increase by anywhere from 4 to 8 times. Okay, so if typical cardiac output's 5 liters a minute, that means you can get 20 to 40 liters a minute. That's a massive amount of blood that's going through your heart. Okay, 40 liters a minute, 40 liters is essentially 10 gallons. So you've got 10 gallons going through something that's the size of your fist. Okay, and so we're going to be focusing on how we can meet these 3 demands or make these adjustments. Now, to help us understand that, we need to know about Mr. Fick. Okay, and so he came up with a law. It's called Fick's law, and it's simply this: VO2 equals cardiac output times the AVO2 difference. So VO2 is just the amount of oxygen that we're using, not taking in, but using. Okay, and this should be taken up or utilized by the tissues. All right, it's not how much we're bringing into our body. Q is cardiac output, and then the AVO2 difference, and we talked about this last week, I believe, what is just how much are the tissues taking up, or we need to know what's in our arteries and then what's in our mixed venous blood. And that will give us an idea, or let us know how much oxygen we're actually using. Okay, but we need to know everything that's going on. So we're gonna go through an example here. So we're gonna use math, and I know that a lot of you don't like math, but we're in a science class and math is needed. So let's say you go running and the following happen to be true, okay? Or this is what you experience. So your heart rate gets up to 180, your stroke volume is 200, and your AVO2 difference is 15 milliliters of oxygen per deciliter of blood. Okay, remember, units are your friend, okay? And we've got some different units here, all right? So we've got beats per minute, we've got milliliters of blood per beat, and we've got milliliters of oxygen per deciliter of blood. So the question is, what's your VO2? Okay, and so it's really quite simple. It's 180 times 0.2 of a liter of blood per beat, so we've just converted this to liters, times 150 mils of oxygen per liter of blood. Remember, there are 10 deciliters in a liter, so we just multiply this by 10, okay? And 200 mils is 0.2 of a liter. And so if we do that, your VO2 is 5,400 mils of oxygen per minute, or 5.4 liters of oxygen per minute. Or another way to look at that is that's almost 1.5 gallons of oxygen that you're using every minute. This is a really high number, okay? And so you would be an elite athlete, okay? Especially if you're on the smaller side. So as you guys have talked about in lab, or at least I believe you've talked about in lab, remember, there's a difference between absolute and relative VO2 max. This is absolute, or relative or absolute VO2. This is absolute, okay? If we want to know relative, we just take this 5.4 liters, and actually we do 5,400 milliliters, 5,400 milliliters. I'm not going to do all the units, but you need it, so that's a comma, by the way. And you divide it by body mass, okay? And so let's say that you're something like 81 kilograms. I can't do the math in my head, so I'm not going to do that. But that's how you'd figure it out, okay? Let's just make it a little easier. Let's just say that you're 100 kilograms. So I'm going to erase this. So if you're 100 kilograms, then what's going to happen is your VO2, your absolute or your relative VO2 would be 54 milliliters of oxygen per kg of blood, milliliters of oxygen per kilogram of body weight per minute. Okay, and that's really good. Okay, so remember with oxygen content, we did this the other day. So just a refresher, the formula is 1.34 milliliters of oxygen per gram of hemoglobin times hemoglobin concentration times saturation. This is where most of your oxygen is, plus 0.03 times arterial oxygen, or the pressure of oxygen in the arteries. Okay, so our content, and this would actually be capacity if it's this way, is 20.4. All right, so remembering that, look at this figure for a second. Okay, and think of this as oxygen uptake. So how much oxygen you're using. You could look at it in terms of intensity too. So this is rest, and then at the end, this will be max exercise. Okay, and so we've got 4 different variables here. So we've got the red line, which is arterial capacity. Okay, we've got blue, which is the actual content, and then we've got this magenta or purple or lavender-ish line, which is mixed venous content. And then we've got over here, and I'm just going to circle this here, this difference between content, arterial content, and mixed venous content. That's our AVO2 difference. So when we exercise, what happens to each of these variables, to each of these 4 variables? Okay, capacity actually increases a little bit with due to hemoconcentration. Fluid leaves the plasma. We can lose it via sweat. It can go into the tissues, that sort of thing. And so as a result, we have our hemoglobin concentration will actually go up slightly. Okay, we're not producing more red blood cells, but it will increase a little bit. Okay, content stays relatively constant because saturation stays relatively constant. There might be a little bit of an increase, and that is in part due to this hemoconcentration. Mixed venous content decreases because we're using more oxygen. Okay, as we exercise, especially if we're running or biking or something, those tissues are taking up more oxygen, which means the amount that's in our venous blood, the amount of oxygen that's in our venous blood will decrease. And so as a result, our AVO2 difference increases. Okay, exercising muscle, especially large muscle, will cause us to use a lot of oxygen. If you look at it here, what are we at? This is probably 18 minus 12. So here our AVO2 difference is about 6. We're still at 18, maybe a little bit higher, maybe 19. Okay, but now we're down to just below 3. So this is like 15 to 16. Okay, we've increased our AVO2 difference by 3-fold. So when we go from rest to exercise, we have to remember a couple things. So heart rate increases with work intensity. So the harder you work, the higher your heart rate goes until you reach max. A good estimate, or generally accepted estimate, is 220 minus your age. Stroke volume also increases with work intensity. However, the max stroke volume occurs once we hit about 40% of max. Elite athletes, it actually will occur later or at a higher intensity, but most of us between 40 and 50% of max. Okay? And cardiac output increases linearly with work intensity, which we just talked about, and the AVO2 difference also increases with work intensity. All right, how do we accomplish all of this? Well, we have to increase sympathetic activity. We have to have our heart have greater cardiac output, which is what the sympathetic nervous system helps accomplish. We have to make sure that that blood goes to the places that we need it to go, right? I don't need to increase blood flow to my intestines during an exercise. I need to get it to my legs, all right? But then the other thing is that we need to make sure that we get it back to our heart. And that's where the pumps come in that we've discussed already.